Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Very well. Anyway. Well, I guess we're going to start. It's my pleasure to introduce Adrian Hilton. He is a professor of computer vision and graphics at Surrey University in the UK. He also heads the visual media research group there. Adrian has done a lot of work on range data analysis in the past, and more recently he's been doing a lot of very fantastic work on modeling and capturing people, and he's going to be talking about that today. Adrian.
Okay, thanks very much. First of all, for inviting me to give this talk, Sing Ben, and for inviting me here. Okay, so what I'm going to talk about today is sort of partly a review of work we've been doing over the last 5 or 6 years on modeling of people, which is sort of at the interface between computer vision and graphics. The motivation really is behind all the work we're doing is to try and bridge the gap between the sort of computer-generated world and the real world. So we're looking at use of computer vision technologies in that sense to try and derive models, or looking at different capture technologies. So the structure of the talk, I just want to say a few words about where I'm from. I thought that was appropriate. And then I want to get right on and talk about the sort of objectives of our work, which I've termed here capturing people. Talk a bit about the background to that, which is the work we've done probably over the last 5 years in that area, and some of the things we've learnt from that, which really motivates where we are now, which is this surface motion capture, which is what I want to tell you a bit about today, and how we can animate people directly from surfaces, as opposed to the sort of conventional approaches to animation, if you like. So first of all, my home base is the University of Surrey in the UK, and I'm part of the Centre for Vision, Speech and Signal Processing, which is one of the largest computer vision groups in the UK, probably of a similar size to the Oxford group, but we're all located in one location, so more of a centre than their structure. We have about 12 academic staff, so lecturers or assistant professors, they would equate to, and professors, and made up of both postdoctoral researchers, and roughly half the group would be PhD students working with them. And then we're split down into 4 groups covering everything from medical imaging through to sort of computer graphics, which is the last topic on there, and including audio signal processing, other forms of signal processing, seismic data analysis, and things like that. And within that group, we also have some very nice facilities, which are what I've been using in my work for things like HD broadcast capture, broadcast quality HD capture within the studio environment, motion capture, and also shape capture of various different forms. And we're located just outside London, so roughly 40 minutes on the train. Okay, the activity I'm most involved with is the visual media group within that. The groups that we have within the centre are basically rough groupings of people. So there's 4 academic staff involved with that, who also have interests in other areas within the centre, so it's not exclusive to them. So we're doing things like visual content production, so content production for the entertainment industry. That's centred around, and that's what I'll talk a bit more about today, particularly the studio production work we're doing. We're also doing things like content production in sports, so technologies that would go into use of live sports, and we're working with people like the BBC on tools that can be used directly in production. there's an increasing amount of work in the area of visual interaction, which includes things like sign language recognition, so tracking of and interpretation of movement, and things like modeling of the face for visual communication, so trying to model very realistic facial dynamics. And that sort of comes into the area of both capturing the face from video or from 3D and trying to represent that in a form that can be used for synthesis. Visual scene understanding, so things like automated recognition of the point structure in sports matches. So this is an example of tennis where we can automatically score the game from video footage. And also things like recognition of sports. So this kind of work is for, again, with broadcasters for analysis of archival footage and things like that. And then the final area within this grouping is things like video coding, so looking at different codecs, MPEG-4 type coding for sports analysis, and also restoration of archive footage. So the BBC, for one, have a huge archive of television footage that they'd like to restore, but it's very grainy. So we have some. Yeah, go ahead.
Sports recognition. Are you saying, oh, this is a track and field event?
Yeah, so we did some work. We did a large work looking at the Olympics and trying to just designate different sports from the video footage. Yeah. Of course, you could use all the secondary data and the commentary and things like that to recognise the sport, but this was particularly on the visual data and looking at what features you could use for that. Okay, so that moves us on to the thing I've come here to talk about really today, which is the problem of capturing people. So in essence, what we want to do is be able to point a camera or a sensor at a person and capture highly realistic models of them. Now the key to this is what we're trying to do is to capture a model that you can then use for production work. So you've got to be able to then control that model in some way. So control it or edit the movement, change the viewpoint, for instance. And you really want to reproduce all the things that go into a real person moving. So things like cloth and hair movement, face movement, all of those things. Now I wouldn't say we're at the stage at the moment where we can do all these things, but we're progressing down that line. We also want to derive some form of compact representation if we're actually going to it's going to be useful for anything. And one of the problems that's, I believe, still very open is we want to do relighting, essentially. And that's something I'm not going to talk too much about, but it's very much an active area of interest in order to composite the models we capture into other scenes and to do that realistically. So there's the immediate applications for this are perhaps in the games industry. We've had technologies for a while that can deliver models at the same quality level as current games. The challenge is to really go beyond that and say, can we get something that really looks realistic? And that's what at the moment is too expensive to produce manually within the games industry, and we don't have capture technologies to do either. And also, there's an overlap there with, if we have these production technologies and they're good enough, then they may also get used in other forms of content production. For instance, in broadcast, we've looked a lot at studio production technologies that just allow much more flexible production. So, for instance, you want to change the camera movement in post-production. How do you do that and maintain realism and make it automatic? You can do it with a lot of manual work, but it's very difficult to do automatically. And the other area would be visual interaction, so mainly the face or the face and upper body, but trying to have automated systems that allow you to interact at a distance very realistically. And that's something, again, that's very difficult to do at the moment. So we can look at some of the previous work in that area. And there's sort of two approaches that have been taken. First of all, what I'm calling here model-free approaches, which really started with the sort of virtualized reality work of Canade back in the mid-90s So a lot of cameras capturing a person moving and then basically reproducing that in some way, which allows you to do things like changing viewpoint. So at that stage, they were using visual hull and stereo techniques. The models weren't that realistic. More recent work, for instance, the work from the labs here, have achieved much higher visual quality. And this is just an example of some of the work that we've done in our labs. I think it was 7 cameras over sort of 120 degrees to do automated view interpolation and pick up things like hair and clothing movement. So the problem is, we can use these kind of techniques, but what you end up with is something you can replay, and you can't really modify that in any way. So it's a limited utility really in content production. So the alternative approach to that is to take a model-based approach. So to say, well, what I want to end up with is some form of structured computer animation model. I know what structure I should take. I usually want a skeleton with some skin on top of that that I'm going to animate. And various people, including ourselves, have looked at that problem as well. Of course, it gives you a nice structured representation, and you can then, from that, modify the movement. So you can capture and modify the captured movement. But today's results are that the visual quality of doing that is relatively limited. Essentially because you're making assumptions when you use a model about what the shape is of what you're seeing. And very often, those assumptions are quite invalid. For instance, long hair, in this example, would be a problem. You know, usually the models don't cope with long hair or long skirt. Of course, you could try and put those things in, but you know, you've got a sort of endless line there of details to put into the model for particular individuals. So the goal that's not addressed by these approaches at the moment is achieving things like a video quality reproduction. So I think certainly the work of Larry Zitnik was, I would say, video quality in terms of changing viewpoint, but there's no ability there to control the movement. So you want video quality and at the same time be able to control it as you would an animation model. You want to capture everything that makes that model real, which is all the dynamics of the appearance and of the shape underlying that. And in the end, you want a structured representation that will fit into the animation pipeline. If you're ever going to get anyone to use this, then you have to realize that the end users, which are the production companies, won't do anything with it unless you've got it in a form that they can talk to. And that's a practical limitation. So I just want to sort of review in a bit more detail where we are with these two approaches in terms of our own work. So the model-based reconstruction methodology, which we and others have developed over a number of years, really starts from some prior knowledge of what you're looking at. So in this case, we're looking at a person. So you have some geometric scene structure. You can also put in some kinematic constraints on how that person's allowed to move. And you may also have some model of the behavior of the person or the movements of the person that you can put in there as priors. Perhaps you get your behavior priors from motion capture data and things like that. So you can use all that information. And the essential idea is then to map that generic model onto your observations of the scene. So single or multi-view camera observations, and then derive a representation from that represents all the detail that you've got from the scene. So this is something we looked at between about 2000 and 2003, I think. We sort of wrapped up this work, which was going from, in this case, multi-camera observations. We've also done it with single cameras, imposing a model, and then coming up with something that you can animate from that. I'll just show some examples of what that gives you and what that doesn't give. So the idea is that you have, as your input, you have some images of your real object plus the generic model. Then you go through a series of stages. So in this kind of framework, I've just outlined the stages here. So you want some pose estimation, essentially. And that might be motion tracking from the video. which is the way we've tended to do it. Then you have a model fit to your observations. So we developed, like others, shape-constrained fitting algorithms, which use your prior knowledge of what the scene shape should be, what a person's shape, and how it varies. And you may use a statistical model for that, differences in body shape. And essentially you fit based on your image observations, usually silhouette, stereo information, anything else, features that you can derive from the images. So this is assuming perhaps a calibrated camera setup. What we've tended to do is if you just directly fit a model, you find you completely over-smooth your data. So you need some representation on top of that. And we've used displacement mapping techniques, as have others, and also texture mapping to model appearance. So these are not uncommon techniques to get this kind of representation in the graphics pipeline. And then finally, you can, once you've got that reconstruction, you can then animate to generate new images. So you can animate directly from motion capture data, for instance. So this is the results I just showed you. This is from 13 cameras, and you get something like this. So I just point out some of the sort of limitations with this, things to note. So for instance, the hair is oversimplified, the face is perhaps oversimplified. In this case, there's a view-dependent texture map, so you're actually picking up some of the changes in appearance as you go around. You can see there's no sort of fingers on the hands here. This was done from standard definition video, so you tend not to get very much detail. For instance, the fingers were 1 or 2 pixels wide, typically in these images.
What's the input resolution?
So these are 720 by 576, so PAL resolution images for this, which allows you. I mean, you get reasonable detail on the clothing. And here she's wearing some quite distinct clothing, but on the face you've got sort of 30 or 40 pixels, and it's really not enough to do any well, you can't zoom in on the face, for instance, but even to, when you're capturing whole body, to reconstruct the face shape is a real challenge at that resolution. Now this is a sort of just a comparison of what the different techniques that you've got, if you like, from computer vision give you. So if you start on we've got the original images over here. These are sort of visual hull reconstructions where you're just intersecting silhouettes. And you can see that you get quite a blocky reconstruction. You don't get the concavities in the surface. Photo hull where you're doing, well, essentially color consistency between the cameras. You get a similar result, maybe a little more detail. It really depends on whether you've got bright colors in the scene. Bright, distinct colors will work well. If you've got sort of shading and things, they don't work so well. You can end up with holes going right through the model. The interesting comparison here is with sort of non-model based stereo techniques, where you start to see the limitations of this kind of approach. So essentially the limbs are quite thin, and the assumptions you make in your stereo start to break down, if you like, because you've got surfaces facing away from the cameras to do matching. So you tend to get overly thin limbs and things like this. So this is sort of a merging of stereo from different views. And finally, this is what you get with the model-based reconstruction. So I wouldn't say it's correct, but it gets around some of the artifacts that maybe you get with the other techniques. And if we texture map that, then hopefully you can see the most similar to the original images is over here. It does a reasonable job, but certainly not perfect. And particularly if you look at the face here, there's an oversimplification of the detail on the face, where the geometric reconstruction is not particularly good. So that's really just to demonstrate the sort of limitations that we have with these model-based approaches. So if you just take the information you tend to oversimplify, and you lose all that detail of the clothing, the hair, the hands. So essentially it's not video quality. And these models are not going to be used in sort of broadcast or film production. You might say, well, they're sort of at the level you could use in games production. They're roughly equivalent to that. But we wanted to go further than that. So what we looked at following that work was really model-free reconstruction in the same way as it's been looked at here. So the idea is, essentially, you don't use your prior knowledge of the scene. You say, I'm going to reconstruct what I see in the scene to remove the limitations of the model-based approach. And with that, you throw away your animation structure, unfortunately. So the framework we came up to do that, which seems to work quite well for sort of whole body modeling anyway, is to start off with an initial shape reconstruction from silhouette, which is quite a robust technique, and then to optimize that based on stereo reprojection to essentially allow us to do wide baseline stereo by starting from an initial coarse approximation. And this is something we found that has worked quite well in the studio work for people, and we're also now applying this in the sports domain for football analysis and view synthesis in football, which is a very different problem, but it's quite a general framework to deal with things where you don't have a prior model. And what we found worked well within that, and the results I'll show you here, are a view-dependent optimization. So essentially you say, this is the viewpoint I want to generate. Now give me the best reconstruction or reprojection to this viewpoint, combining all the images as best you can. So these are some images just taken around a semicircle, automatically generated. So we're doing a surface reconstruction. And then you can see the two examples. So this one is just panning across the scene, so interpolating essentially between the cameras for a single time instant. And you can see a reasonable reconstruction of the pattern on the dress and things like that. And actually, as far as the studio work goes, this is at standard definition. This is good enough to start being used in a production sense. But the big limitation is you can't manipulate the data very easily.
So you also have temporal consistency?
Within this, there's no temporal consistency, actually. So that's one of the issues I'll come on to. Yeah, there's reasons for there not being temporal consistency, which is essentially that if you impose smoothness constraints over time, you tend to oversimplify the detail. So we actually found that imposing that simplicity loses a lot of the detail that we want to reconstruct. Now you've got a sort of 50-50, because when you generate sequences, you actually want the temporal consistency. So it's something that should be in there, but we didn't want to do it within the same framework of a sort of smooth, deformable surface that we're using here. These are the same kind of technique, but what we've done here is a pre-computation, so these can actually go into a games engine or something like that. And what we think is that so they're essentially a representation that's optimized for view synthesis from all viewpoints beforehand. So we've captured movements of people, again, within the studio environment from cameras all around them this time. So about, again, 8 to 10 cameras for these shots. And this is the sort of character that you could start to use in a game environment as a cutscene. You can't manipulate them, so it can only be used as a sort of pre-computed or pre-stored rendering, but potentially for a cutscene where you can navigate through some dynamic information. And you can see the visual quality of these, particularly this one, is pretty good. I mean, the quality of the face there is quite reasonable. You can see there's a little artifact between his legs, and there's a sort of striping going up the side of the body where there's slight reconstruction errors still. Just to look at the model-free technique in terms of what we're doing there. So you can see, again, this is the visual hull reconstruction, relatively blocky. If you do just straight stereo, you get a lot of artifacts. Trying to do this kind of wide baseline stereo, the views are still quite widely spaced, sort of 30 to 45 degree views. And And what we're getting with our technique is essentially something very smoothed, but it reproduces a reasonable rendering. So this rendering is quite close to the original over there. Okay, so we have, at this point, two approaches, which both have their advantages and limitations. So the model-based approach, essentially you have a loss of detail of the things we want to reconstruct. And the model-of-free approach, you have all the detail, but you don't have any structure. So we got to this point roughly 18 months ago, I guess, and said, where do we go from here? What can we do about this that tries to capture the benefits of both of these approaches? Okay, so this is where we come on to trying to animate things directly from surfaces. So the thing we know we can capture is this sort of model-free surface reconstruction that we know we can do a good job on. Yeah? So we've termed that here surface motion capture. So we can do a model-free reconstruction of various different movements of a person in the studio. And we can represent them, or I'll show in a minute how we can represent them in a consistent temporal structure. Okay? So the problem then becomes, well, how can I then do any form of animation from that? How can I recontrol? So what we've developed is a sort of example-based animation, which is analogous to the example-based animation techniques that have been used in video, for instance with video textures and things like that, and also the motion graph work where you're animating from motion capture data. Except that the examples here are sequences of surfaces over time. So the idea is that you take your actor into your studio, you capture a set of different sequences of different movements, and then you want to build a representation that allows you to go between them in some way. So this is exactly the same as you do with MoCap data in a game studio. You capture a performer performing various different movements, you'd capture the skeletal motion from that, and then you'd transition between those skeletal movements to make up your animation. So what we're doing here is trying to do exactly the same thing, but now with surfaces. And the key problem is how do you build these links between the different surfaces? How do you build the graph so you can transition without introducing artifacts? And that's what we think we have at least an initial start of an approach to do. So just to run through in a bit more detail what we're doing here. So the first step is just the surface motion capture, and that's really what I've talked about already in terms of model-free capture. We can employ all those techniques from computer vision for reconstruction in that sense and obtain the best reconstruction that we can from that. Best in terms of quality when you reproject to the original images, usually. But at that stage, it's unstructured. Okay? So the first important step is to then go from that to some form of structured representation. And what we've used for this is to use geometry images. So a technology that was developed by Hughes Hoppe and others here was to represent 3D geometry essentially as images. So this is a geometry image, single frame, and a texture that goes with that by mapping onto the spherical domain. So the first thing we do is unfold our sequences that we've reconstructed into the spherical domain. And that's very nice because it gives us a structured representation immediately at that point. So we know how many polygons we're going to have in our model at each frame. We can represent it at different resolutions, reproduce different resolutions very easily at that point. So that's the first step. Then the second key step is then to build this graph, this surface motion graph, so that we can actually animate from it. And that, if you like, is the more difficult problem of trying to define these transitions between the surfaces. And what we've looked at doing is, again, using this spherical domain that we have, so that rather than matching in 2D, in 3D, we can do our matching in 2D on the surface of the sphere, in terms of matching between different surface sequences. And I'll talk about that in more detail. And then finally, well, once we've got to this stage, we can then interactively animate the character based on user controls. And I'll show some examples where we've done this for various different characters. One important thing to note is, so what I'm saying here is that what we want to do is go from the surface capture. And that surface capture will contain all the cloth movement, the hair movement, everything you've reconstructed from the scene. So when you animate down here, you should have all that encapsulated within the representation. Now that has certain advantages in that it looks realistic in the sense of the original capture, but certain disadvantages in terms of it's completely different technology to what production pipelines are used to. So what I'm proposing here is something quite different from the conventional animation from skeleton type pipeline, where you animate from a skeleton and then you put cloth dynamics and things like that via simulation on top. Okay, so just briefly, the surface motion capture really goes from a studio with, well, the results I'm showing are either using 10 standard definition cameras or 8 high definition cameras. We then have a reconstruction technique, which I'm not really going to talk about too much. It uses essentially the best of the algorithms that we've been able to find or develop in the computer vision literature. And at the moment, we're using a global surface optimization that takes into account stereo, silhouette rims on the surface where the silhouette touches the surface, and also feature constraints. And at the moment, this reconstruction is done on a per frame basis. So what we end up with from that is really the unstructured mesh. You can see that's a single frame of it shown on the right-hand side there. Okay, so the next step is to put that into a consistent representation. Now, when we did this first, and we first used geometry images and mapping onto the sphere, we did it with just genus 0 surfaces, so all our people had to stand so that they weren't touching themselves. We then developed it to handle arbitrary surfaces, essentially, by cutting the original mesh. So the first stage, when you've got an input 3D mesh sequence, the first stage is to cut your genus N sequence in a consistent way so that you can map it onto the surface of a sphere. So essentially to put some holes in the mesh that allow you to do that. And then we're essentially using a chain of algorithms that have been developed by others. So the first stage would be a progressive mesh decomposition. Now this is quite important for our work, not just here. We're just using it in the geometry image sense here. But it will come in later when we do the matching algorithms and temporal matching as well. We've made use of this kind of hierarchical decomposition where you go from the detailed mesh down to a tetrahedra, essentially, decomposes to. Okay, so the spherical mapping just takes that decomposition and then maps that back onto the surface of a sphere. So at this stage, we've got all the detail from the top guy mapped or embedded onto the surface of the sphere without any overfolding of the surface there. And this is essentially the geometry image framework previously proposed. So at this stage, you get at each frame, the representation in a 2D image format. And the only thing you have to be careful about here is how you do the sampling, because you've got now the reconstruction with something with long, thin limbs. And if you do it naively, then they're going to become very small when they're mapped onto the sphere, whereas they've got a lot of detail. So you have to adaptively sample to represent that detail efficiently. Otherwise, the resolution you required here would be very high in your image format. Okay, so for each input sequence at this stage, we've got now a geometry image sequence. And you can see here that these things are jumping all over the place. In this process, it's done on a per frame basis. And there's nothing that constrains where different body parts essentially go in here. So that's something we're going to have to take back out later. It's difficult to do that within this framework. It's a very generic framework for mapping from 3D to 2D. Okay, so perhaps the most important part of this is the surface motion graphs. Now this work really derives from motion graphs introduced based on skeletal motion by Gleicher and others, which allow you to do essentially take a database of skeletal motion and resample from it. So to sample segments from that skeletal motion to produce new motions and motion transitions. And this technique is what's used a lot in games animation. So essentially you take your performer into a studio, you capture a set of movements and movement transitions, you build a graph from that, and then you can animate that character and transition between them. And what we want to do here is the same thing, but for our surfaces. So the key problem becomes, how do we do the surface-to-surface transitions where we're talking about transitioning from one surface sequence onto another one without producing artifacts? So what we'd do is to capture a set of movements. So, well, these are some examples that for one character we captured: walk, run, turn, kick, idle movements. Then the problem becomes, how do I define the transitions between both different motions and between to make cyclic motions? So our studio is about 2.5 meters long, but I want my person to be able to keep walking indefinitely, so I've got to have cyclic transitions within there: walk to walk, run to run. So the way we've gone about doing that is in 3 stages. The first is to identify similar frames. And that can either be done manually by saying, okay, these are key events, the start of a walk cycle and the repetition of a walk cycle where it would be good to match. Or they could be done by similarity between the geometry and appearance at those points. There's no reason why you couldn't build the graph structure automatically from this. Then the problem becomes, well, okay, they're going to be similar, but they're not exactly the same. So you then have to estimate the correspondence. Okay? And if you can do a good job of that non-rigid correspondence, then when you transition by morphing between the two, you're not going to get too much deformation of the surfaces. So you really want to align the body, the points on the body are the same points. And also for the textures, you're not going to get too much blur when you transition. So the key step is this number 2 here, if you like. Okay, so the problem is then, how do I get, for these 2 different movements, I've identified that I want to transition somewhere in this part here, between these 2 sequences. How do I then define a similarity between these 2? So you can see they're similar, but they're not the same by any means. So his arm here is a bit lower than it is here, for instance. So I have to align that so that the hand on both of them are in the same place, the arms lined up in terms of the geometry. So I want to define a transition window across which I've got correspondence between the 2 sequences. And I've got to have some way of getting that correspondence. So the way we've looked at doing this in the case of a genus 0 surface is to use this spherical embedding that we've got. So it goes from being a 3D matching problem, where you're trying to match 2 different surfaces, to a 2D matching problem. And within the spherical domain, you can ensure that that's a unique correspondence as well. So the advantage of doing it in this domain is that you can guarantee that you have a one-to-one correspondence everywhere in that matching. So the idea is to take, so you go from your 2 different frames in 3D down into the spherical domain. So you've got those 2 spherical embeddings, which you can see a difference. For instance, the head is in a different place in this 2D domain, the arms in a slightly different place. So we've then got to line those back up. And the way we do that is to optimize for the mapping between the 2. So we're optimizing for a correspondence W, which is essentially a correspondence for every point on one model onto the other, which minimizes the difference between the 2. And here we're taking difference as being shape, color, surface normal, potentially surface curvature. So if that process has worked, what you should end up with then is this mapping W, which takes this guy and maps it to the same shape as this guy.
So, in the so there's two spheres. There's a texture sphere and a geometry.
Uh-huh.
And since the original mapping from your capture to geometry is done frame by frame, it seems like those signals are drastically different.
That's right, they do, yeah.
That really have almost nothing to do with each other. And so
Well, okay, they have, that's right. So they're not aligned in any way when you do the geometry image or geometry video sequence. But what happens is, so the first component, and I'll show an example on the next slide, is that you get a rigid transform that essentially lines them up. So it will line the head up to roughly the same part. And so what you're lining up at the same time is both the geometry and the texture. So I'll move on to the next slide and I'll try and illustrate what I mean by that. Come here. Okay. So this is showing the non-rigid alignment process between these two guys. If you look back, so what we're doing is doing it in a hierarchy starting from the lowest resolution. And you'll see right at the beginning there, it does a rigid transform, essentially, round. So by using the hierarchy of your progressive mesh structure, it actually gives you a very powerful mechanism for transforming between two things that are a long way from each other. Now, you're still going to have difficulties if, for instance, you take someone doing this and match them to someone doing this. Then the problem will be that there's a large non-rigid component there, and it will still match it up, but the transition you get between the two isn't going to be particularly sensible. So that's why I'm saying you need to have similar poses to get a reasonable transition. So to get around those problems, we have a sort of coarse to fine matching to get around, well, the partly self-imposed problem that you've completely misaligned them to start with. And actually that rigid transform just drops out on the first iteration.
in terms of the search for where there are matches, you're doing that by hand right now, saying try to match these two?
So yes, we are. So in the work we've done, what we did was, because we just got short sequences, we said match the end of this sequence with the beginning of this one. So we define the overlap manually. Now you could look within the spherical domain. You could look. Well, the other thing we have done over sequences, I'll show an example in a minute, is match whole sequences together, and there you could look for what's the similarity. Essentially, if you could align any frame with any other frame and say what's the non-rigid transform that gets me from here to here, and if that's large, then it's probably not a good transition. Okay, so if we get onto this frame, unfortunately I don't have the video for these results, but you can see this is the results of the non-rigid matching. So on the top, what's shown is just points picked out on one example and mapped over successive frames to give some idea of what's going on. So for instance, if you look at the foot point here, it's lining up fairly well all the way through the sequence. These guys are quite nice. So these are points on the hand where it's lining up right through the sequence. So this is over probably 50 frames or something like that of a sequence. And the results on the bottom here are just, we can take that result and impose a skeleton on that fairly easily, which wasn't the purpose of doing it. But if you do, you can reconstruct the movement. So you can see here the sort of hand movements coming out of this. So as a byproduct, we've got a sort of markerless motion capture, video-based motion capture. Although you may argue whether it's the best way to do that, but it certainly gives you that within the alignment. What you will find within here, if I talk about the limitations of the alignment, is, for instance, on the trousers here, you've got a very large smooth region with really no appearance variation or shape variation, and their points are going to drift around a bit because there's nothing to constrain them. So your non-rigid alignment there may not be physically correct. It will just be down to the constraints you imposed in your matching algorithm.
But when you do interpolation shape, don't you get unnatural shapes in between sometimes?
Like when you're doing here and here, you might just go from straight up here, so the limbs might be short and unnatural.
I think so. You would if they were too far apart. That's right, you would, because you're doing a linear interpolation of something essentially that's non-linear. What we've done to get around that is to look for things that are fairly similar. So if you match from this to this, you'll get something slightly odd in between. If you just do a linear sort of morph between the two.
Even something that's fairly close like this. I mean, you might.
So in that case, well, you can judge the results and see what you think. I mean, this is an example. There's some flicker in the video here, but it's an example going through between these two sequences, and they're aligning. You can see the overlap region here. That's not really that close in alignment. They're roughly the same pose, but hopefully you don't see that within. You don't see a jump or a sort of arm shortening within the video. It seems to work quite well. What we haven't tested, I suppose, is how far you can push that. We know we can break it, but how far that will go. So this is spherical matching over a small window in time, essentially. And that allows you to construct then this graph, and I'll show some results based on that. So here we've captured, I think, 5 or 6 movements, so we've got turning movements there as well, walking, running, that sort of thing. So this is a single character, just a video of that character going through various different movements here and turning. So you can see, if you look at the legs, you can see that a lot of the deformation of the clothing and things like that is preserved within the model. Now you might say, well, this looks just like I could animate that with a normal model, computer character model, and I would have to agree with you at this point. Hopefully I'll show you some examples in a little while that would be a little more difficult. Just well, we're showing these. So this is 2 more examples. All of these are animated in real time once you've got the model reconstruction. So I think, well, we're using up the whole budget of the graphics performance here. You can show various different animations can be created like this. So this was our sort of proof of concept, if you like, results from, well, last summer, really. One of the things that Singbin mentioned that's missing here is any sense of temporal continuity. And we didn't put that in the framework because if you do smoothing over time, it can create some very odd results. And in fact, when you look at people moving, particularly with non-rigid clothing, the clothing moves all over the place, and you're probably not going to be able to match very accurately over time. Things appear and disappear. So what we've done to get around that is to have some temporal matching as a post-process, if you like. So in the case of a genus 0 surface, then you can use the same framework essentially and match over time, which is the results I showed you earlier. If you've got a genus N surface, then you're in a bit more trouble in terms of matching because you've imposed cuts on your sphere. So in fact, for that, we go back to matching in 3D over time, where we've got reasonably similar poses, and we do a non-rigid match there, again in a coarse-to-fine framework. So coarse-to-fine deformable surface, and I'll talk a little bit more about that. Once you've got the temporal matching, then that allows you, of course, to do things like low-pass filtering. So the reconstruction results I'll show you next were captured with 8 cameras, and there's certainly some visual hull artifacts and things like that coming out on them, where you've just got occlusions from the different views. And that allows you to get around some of that, and also any sampling errors that you might get. If you've really got temporal alignment, then of course you can do editing, and you get a consistent representation, which is something I think that's important if this is going to be used in a production pipeline. So just briefly, for the genus N surfaces, what we're doing is a multi-resolution non-rigid surface matching. And what we found we need to do is employ quite a lot of machinery, if you like, to get robust matching. for this. So we've again used the progressive mesh hierarchy, and essentially at the lowest resolution what we're doing is a rigid alignment between the two. And then we're using both multi-resolution deformable models, so starting from coarse to fine, and multi-point matching techniques, which allow you not to just define a hard one-to-one correspondence to start with, you just define a one-to-many correspondence and then refine that as you get closer to the match. So these are sort of robust techniques. Now, the problem with doing deformable, if anyone here has done 3D deformable surface matching, is there's no guarantee of one-to-one matching, and you can mismatch small bits and all this sort of thing. So that's why we went for the 2D framework, because it gives you some guarantees. Within 3D matching, that you don't have those guarantees. So sometimes this will break along with every other non-rigid surface matching technique, I think. Within this work, what we add at the end is sort of a refinement step, which is to essentially go back to the original images and do correspondence again between the original images to get sub-pixel alignment. So in order to get really good alignment over time between the texture information, what you do is go back and reproject your surfaces into the images and actually match the original images. So just to avoid any loss in the system and lock it down as far as possible. Okay, so this gets onto some of the results that this was done with 8 cameras from 8 high definition cameras now. And I'll show a little demo in a minute. So what we've done is capture this dancer in the studio. And this is showing one movement from the capture, and obviously freezing in the middle of the movement. And you'll notice here there is a lot of cloth movement. I mean, these are quite dynamic movements as things go. But we've been able to do a reconstruction from that and even animate from that. So this is now... that's not. I'll just switch my screen. Okay. Instead, we'll go to the demo. So that's even better. Okay. So this is another character, obviously, with a long coat. And this is running just on this machine, so I can change viewpoint, for instance. So what I want you to notice here is, for instance, that the coat is a loose coat on the person. Let's just get the guy to turn around a bit. Okay, so you should be able to see that the corners of the coat actually are out here. Now, if we'd used a model-based technique, that would have all been mapped right down onto the person. We'd had, well, with any of our techniques anyway, we'd have had no chance mapping that. So I'm just changing his orientation there. We can obviously pan around him. And I think this guy's running at about, on this little machine, about 60 frames per second, something like that. This is in a games engine. We should be able to get, yeah, so the Axiom games engine. You can see there the refresh rates on that. Ooh. And I should be able to just change the rendering mode. And you can see roughly the polygon resolution there. You may not be able to see it on that. Display's not quite so good there. That's just the individual polygons. So now you'll see it's slightly pixelated. Okay. Now what I can do is change their transition between the walking and running. Let's transition back to walk. Let's try that again. Okay, so all this is showing really is that we have a controllable character. I'll just change the model there. On the platform, and again, this is one of the movements from this guy. And you can see a lot of clothing dynamics there, which are hopefully reasonably well preserved. You're welcome to come and have a play with this afterwards. To have a look at on the screen here, where you've maybe got a little better resolution and on the screen up there. I guess one or two caveats I'd add in what I'm showing you there. At the moment, we're just deriving a single texture map, and it's in this geometry image representation. We think we could do better if we put in things like view-dependent rendering, less loss of detail, I guess. I'm just going to skip through those. Well, just some things to say about processing times and things like that, because I'm sure I'd get asked these questions. So the single largest time is the capture time. Setting up a studio with 8 cameras is not trivial. Doing the capture, getting the performer in, getting it all working is certainly by far the largest time. These are sort of rough reconstruction figures for each step. So you can see there things like the matching step here are quite expensive, not incomparable to some of the other things. In terms of representation, this is for a 256 squared. I think the final one I showed you there is a 512 squared image. You're on something like 0.4 megabytes per frame, which does add up. These are larger than you ideally want. The motion graph there was somewhere around 40 megabytes for those characters. And even in our sort of initial implementations, they can run in real time, as I just showed. Just looking at the resolution issues, this is sort of the characters I showed you where I showed this guy were about 256 squared. We're actually using 512 squared at the moment. There's obviously some redundancy in there where you've got uniform areas versus where you've got detail and things like that. There is an adaptive resampling, but it doesn't perhaps go far enough to represent all the detail on the face, for instance. Okay. So just to sum up, really what I've tried to do is show 2 different approaches that we and others have developed for modeling of people, capturing people, and to say, well, both of them have their limitations. Neither are good enough. So what we're proposing is to actually do animation directly from surfaces. So to not go via the skeletal route. Because as soon as you go down that pathway, then you're making some assumptions about what you're seeing in the scene. And those assumptions are never going to be valid. You'll take a period drama all of a sudden, and you need to start modeling the dresses and things like that, which defeats the whole object of what you're trying to do. You're trying to have an automated process. So we're rather turning it around the other way and saying, well, go from a model-free solution and then introduce methods for animating from that. And we believe this has something to say in terms of a potential for production, particularly in games at the moment. Of course, there's plenty to do. Well, the easy things are things like view-dependent rendering, although as soon as you put that in there, you've got sequences, so you've got an increase in representation cost. Perhaps the second on this list is the most difficult to deal with, relighting. We've been looking at methods to capture material properties for these dynamic scenes, which essentially fail because the geometry you reconstruct, or the normals in particular you reconstruct, aren't accurate enough. And that's a fundamental problem. Most of the sort of relighting work is done on static, high-resolution object models for the reason that to do relighting you need very high-resolution geometry. So that's an issue, which we think we've got some ideas to deal with, but I'd be very pleased if anyone's got any suggestions for that. Issues of compression. There's a lot more that can be done in that area. This area is perhaps what needs the most attention to move this work forward as being actually used, to try and get this kind of technology, which is quite different from skeletal animation, into a production pipeline. And the key there is really to go back and represent the models in a standard form, but to have these additional layers on top, if you like, that represent the fact that you captured the clothing dynamics. Yeah? So to put in things like skeletons, things like the ability to control the movement, but not to lose the detail. So there's issues here which we're looking at. And then one of the things that certainly comes out from this work is, in terms of the resolution of what you capture, it's never going to be good enough from camera technology. The immediate things, for instance, showing this to game developers is, well, we're used to using 2000 squared resolution textures on our characters so that we can zoom in on the face, and okay, you can increase the image resolution, but you're never really going to win that battle. They want very high resolution on the face, which is not what we're capturing. So we need other ways around that to deal with increasing the resolution in areas of a lot of detail at the same time as doing the capture. And it's a similar problem to the one they have in the motion capture industry at the moment, where they're doing face and body capture at the same time. And they've sort of, well, through 20 or 30 years of development, are getting to the point where they're solving those problems. I think in this kind of video-based technology, that's further off. And really things like hair dynamics, we're not dealing properly with at the moment. Okay, thank you very much.